in person, obviously, so it looks like you have really. Yeah, that'll come. Yeah. So this is supposed to be a really elementary talk about some eventually slightly advanced topics, but we'll start and we'll keep going in a very elementary way. And you'll see. So I don't want to insult anybody's intelligence, but what is the basic interpolation problem? If we have some set of points, we would like to fit maybe points, A1, A2 through AN, and we would like to fit a polynomial of the smallest possible degree to given values. So f of A1 to sub f of N, like a polynomial f of x. Then, of course, there is an explicit formula due to Lagrange, I think. So it says f of x equals summation over I, maybe k, f of ak. Then we put product of over I not equal to, maybe write the product outside. So product over I not equal to k, x minus ai over ak minus ai. And I think everybody agrees with that. And this formula makes sense. So there's two remarks about this formula. First, this also makes sense when AIs collide. Right? So if the sum of them come together, then this formula actually has a good limit, and it's actually this means interpolate not just the values but also derivatives and so on and so forth. So in other words, this is really what this really is an extension. So if you look at the space of all, if I may draw the kind of the caricature, there's a space of this A's, and there is a space, and there's a line of X, and then in that space there's a subvariety, which looks schematically something like where it's the union of things where X equals one of the AIs. It's some union of hyperplanes in this algebraic variety. And the question is extending. So we take a function. So we take a function on this union where X equals AI, and we'll like the function on the whole space. The whole space with coordinate X, A1 through N. That's one thing. And second thing is that some formula like this, analogous formulas, work for. So this was about function defined on a line. So if we had a function on, I don't know how we define the line today. Maybe it's like C or okay, in A1, however you want to define the line. And replaced by the two other kinds of one-dimensional algebraic groups. So you can replace by C star, aka the multiplicative group of the field, or elliptic curve. Right. So this is what we have here is so this is, and the typical expression is it somehow with the elliptic curve is that if instead of having a term x minus ai over ak minus ai, what you should do is you should take the theta function of x minus ai over the theta function of ak minus ai. Right? How some right? So this is basic structure of the formula.
Is there any unexpected in the case when we replace a c by c square?
Well, we'll get to that. This is not the problem. We'll be solving some specific interpolation problem today.
Okay.
And I'll explain where this falls inside, with a few differences. A few important differences. So in the case of GM, we're looking for interpolation polynomial of a minimal degree, but the degree of a Laurent polynomial, this is its Newton polygon. And so everybody agrees that the right, if I have a polynomial, you know, monomial x to the 100, if x is invertible, that has degree of an invertible element has to be 0. So you shouldn't think of a degree of x to the 100 to be, so maybe I'll just write down degree of a monomial, maybe y to the 100. That shouldn't be this shouldn't be 100. Should be just a segment from 100 to 100. Right? So, but then, since the variable is invertible, that means up to shift. So when we're looking for the minimal thing that interpolates given data, that could be done with a certain Newton polygon. But that Newton polygons we can shift arbitrarily left and right, or you know, forward and backwards, and this in principle gives different solutions. So in the multivariate case, it'll be genuinely different things. So genuinely different in the multivariate. And the shift is in the multivariate situation genuinely different in the multivariate situation. And this is a phenomenon as basic as it may seem, actually relates to kind of deep things in math. It relates to all this combinatorics of kind of alcoves, walls, etc. Walls, and you know, all that kind of combinatorics. That's very, very prominent in cardinalistic theory. In cardinalistic theory, another example, there is always this combinatorics of some kind of walls, and then some piecewise constant dependence on certain data, and that very often, particularly in cardinalistic theory, that can be this piecewise constant dependent on data may be traced to the fact that I'm trying to have some window and I'm moving it on a lattice, and as I move on a lattice, some lattice points come in and some lattice points come out, and I look for the corresponding Newton polygon for the corresponding interpolation polynomial, and it changes. And so that's one thing. That, I mean, it's not meant to be an explanation. It's meant to be a pointer to something which may be dear to some of you. And the second thing in the elliptic situation, which will be of maximal concern for us, for E we have moduli for. So for elliptic curve, we're looking. There are no functions on elliptic curve. We have to look for sections of a line bundle. That is to say, what does mean a section? If you think of your elliptic curve for line bundles of degree of some suitable degree, so let's say n. So how we concretely think of, so e.g. for if your elliptic curve is a quotient of C star mod Q to the Z, you can say like this, maybe Q is less than 1 in absolute value, bigger than 0. So then this is a section of a line bundle of degree D are functions satisfying, those are functions satisfying a Q difference equation of the form QFQX equals some constant times x to the minus n f of x. And this constant, or rather its class modular, its class mod Q to the Z. That's a point in the, well, in this case in the dual elliptic curve. So this is a point. This parameterizes, that is the coordinate on line bundles on degree n. So this is a point in, you take the Jacobian of degree n line bundles of elliptic curve, or whatever. So that is isomorphic to elliptic curve itself. So this there's a continuous variable there, and this continuous variable. So then the interpolation is analytic in this variable. So maybe let's constant. Let's denote that constant Z is analytic in Z with poles. And I'll explain in a second what this has to do with poles. You know, what's the meaning of poles? And these poles. So if I have poles, they become the walls as my elliptic curve, this Q is Q to, if I send Q to 0, then or Q to 1, I mean degenerate my elliptic curve. So poles, then this my elliptic curve degenerates to, well, let's say C star in this case. So there's a or you can say a smooth elliptic curve. So this, okay, I should do better work at drawing a smooth elliptic curve. Let me say if I have a smooth elliptic curve, it may degenerate to another one. So that's and so this is the fact that there is analytic dependent. There's an extra parameter that parameterizes. You know, we're trying to fit a section of a line bundle. That is to say, a solution of a Q difference equation. We're trying to fit of a very simple Q difference equation. We're trying to fit it to the data, and there is a parameter. Their result will be analytic, and with the analytical, there will be a pole in this formula, and for the simple reason that why is that? Because if I look at so continuing, we'll say with this example, so solutions. If I look at solutions of these equations, this has dimension. This space has dimension equal to n by Riemann-Roch, or by any other argument that you see in elementary theory of elliptic curves. That is this dimension. This has n-dimensional space of solutions, and interpolation is about the map evaluating it at end points. And the question is whether this map is surjective, right? So whether this map is isomorphism. And of course, the kernel of that so the kernel of this map are exactly the functions that vanish at A1 through AN. All right, so this being space of the same dimension, that this is isomorphism if and only if there's no function that vanishes at this point. But all functions, any such function has to be any function which has solution of a section of a line bundle of degree n vanishing at endpoints, this has to be proportional. This is times product of theta functions. Right? So it's only the question is whether this object here, whether it's a section of the, what is the parameter z for this particular function. So this means this is not a section of line bundle I want unless z is equal to the sum of ai. So when this condition is, this sort of resonance condition is satisfied, this is a section of a line bundle that I want. Because if you have a section of a line bundle, it's a curve. It's very easy to know what is section of. You just sum up the zeros according to the group law in elliptic curve, and so this is a pole informal. So there's this phenomenon that this is, again, the interpolation problem has a unique solution with a pole along a certain specific locus, which is generalization of this. Okay, so that was a review of very, very classical theory, and now we're going to reinterpret it. So now the next step is we will be reinterpreting this. So we had our space with coordinates a and x. My Moscow mobile's ringing. Interesting. Well, and then they had this locus here, which is the union of x equals ai. And so now I'm going to say that this is in fact something interesting, namely the ambient. So there's an inclusion. So there's there's an inclusion map. Let me try it. I don't know why it doesn't. Oh, here. So let me take this. I apologize. My whiteboard skills are somehow failing here. Let me just copy the whole thing and then see if I can erase it. Not sure why. I'll just draw it again. So I'm sorry. This first time my stylus is somehow not doing the operation I want. Just probably has happened to you in your teaching too. So you have this inclusion. So you have inclusion of this set into this ambient space, and interpolation asks for extensions of functions from this closed subset to the ambient space. And then I say that this is in fact, this ambient space is the equivariant cohomology with respect to a certain torus A, and maybe a group, which is called group G, where group will have to do so of just the n-dimensional. Well, let's just stick to non-fancy notation here, where the group, where A is the group of diagonal matrices with coordinates an, a torus, and G is the group of scalars So in this case, it's a very trivial group, but nonetheless. And here, this is the spectrum of that. And this is, and then receives a map from the spectrum of what? Of some open set. Namely, I throw out the 0. And then on this open set, I have my group G acts freely. So this I can say a spectrum of equivariant cohomology. And explain in a minute what's equivariant cohomology. So this is if you're not where. So now if I throw out the origin from the vector space, that my group G, the scalars that they act freely, and so that I can mod out by that. So this is the same as spec of the quotient. And the quotient is then projective space, projectivization of the CN. Okay. And so then the question is, so the question of extending functions can be phrased as extending cohomology classes. So these are cohomology classes. On a quotient, on a GIT quotient. So when we throw out 0, that was the unstable locus. Of GIT quotient, we take Cn mod my group G, and then we would like it to extend them to cohomology classes. On the quotient stack. Okay. That's the kind of question. And now I realize that this
put A here.
What?
When you wrote, okay.
So I realize that this is a certain jump from univariate polynomial term. So I'm going to explain what's equivariant cohomology and how this works. So that's my plan. I just want to make it. If it's obvious, then we'll just. So let's see. If you think it's what I wrote down is obvious, then I'll be happy to go forward, or I'd rather explain. Yes, and I explain in fact, and then with C star and E is the same. The same with cohomology replaced by Equivariant K-theory, analytic cohomology. And so I will explain this. It's easiest. I think it's easiest to explain what's K-theory. So this I will explain what this is. And so what is if I have some topological space with an action over group, so if I have some topological space, I don't know, X, with an action over group G, then I can ask for equivariant vector bundles over that space X. So I can vector bundle over that space X. So point X, and if I have some element that takes it to Gx, then I would like to have a vector bundle which is equivariant under the group. Means there is a linear transformation. There is an action on the total space of the bundle, which is linear on the fibers and covers. So it's like if you have a representation of a group, it's an action on a vector space. If you have an action on the manifold, what's an action on an action on the topological space? But now you have a vector space for every point of your topological space, and the group acts linearly on this vector spaces as it permutes points of the base. Right. So this is if I have a V is a G equivariant. Bundle. on X, it defines a class in this G equivariant K group of X. And this is a ring with operations of, well, there's a direct sum of vector bundles. Then there is tensor product of the vector bundles. And then there is, since it's a ring, this is, well, the K-theory is when you formally add the inverse to the sum. So it's like with you go from natural numbers to the integers, you have addition and multiplication, and you introduce subtraction. So this is something you add in K-theory, some new operation you add. That's a ring. And one can ask is, what is the spectrum of this ring? And this has two nice properties. First, maybe sub-properties. So one first is that the K-theory of a point, well, then we're talking about just one vector representation of group with the operations tensor. So this is the same as characters of representations. Because the operations, if you have a character of representations, they add under direct sum and multiply under tensor product, and will subtract under direct difference, and so this is called representation ring of G. This is the definition. And second is a homotopy invariant, that if I have, so it's a special case of a homotopy invariant, that if I have action on a vector space, so this is, since a vector space is contractible, that is the same as the action on a point before. So in particular, if I have my action, so in particular in this example, if I consider this K and I had this torus A cross C star with the group of just the vector point Cn, well, that's a vector space, and so I get just representation ring of these groups, and so this is just tori, so this would be Z. Well, this is K-theory is defined over integers. In fact, like the whole theory we're discussing here is in fact defined over integers. But so this you can extend scalars if you want to any field you want. But let's say so this would be, what are the characters for irreducible rotation of a tori? Just Laurent polynomials. So this would be the Laurent polynomials, and we were talking about Laurent polynomials. And then there's one more thing for this extra C star. Right, so that's another property. And then third is that if I have a free action, so if G acts on X freely, then K G of X is the same as Kx mod G, and the isomorphism is just the pullback. So this the pullback under this map, it gives this isomorphism. And then moreover, there's a fourth. There is exact sequence. So in algebraic K-theory, let's say there's algebraic, there's topological K-theory. They're all the same in this case. But maybe I'll write it so maybe I'll write it in a slightly ambiguous way. So there is a map. So if I have a K of X, then if I have an open, then there is a map to restriction to the open. So open, G invariant open. And depending if you're topological or algebraic K-theory, it's either 0 or not, or it's either, but it doesn't, let's not worry about that. And then the kernel of this map is the complement, the corresponding closed thing, and then there's a long exact sequence of higher K-theories. But so in our case, this is we're talking about this was X was Cn, and the open restrict to the open was we took the origin, and so then what sits here is then just the K-theory of a point. Going here, sorry, I sometimes drop the sign of the K-theory. And what is this map? This is this map here. So this is inclusion of a representation as a skyscraper sheaf. So it means so you take a representation and you make a skyscraper sheaf at the origin. Oh, that's the map. This is a slight extension of what we're talking about before, in that if I have a say a smooth algebraic variety, that then I have, in addition to vector bundles, I have coherent sheaths. But those I can resolve by vector bundles. So I don't really. So coherent sheaths have their natural K-theory classes. And so in particular, if I have just a skyscraper sheaf, means something, just some vector space that sits at the origin and zero everywhere else, that has a certain class. And what that class is here's the class of that class computed by the Kazura solution. And it equals the product of 1 minus x over AI. Okay. And so this map this is really when you mod out by this relation, modding out by this relation is exactly the corresponding map here. So this map here is a modding out. This restriction to the open, you take mod out by relation, which is 1 minus AI over x. And what does it mean? You mod out function by this relation means you restrict your function to the set defined by this equation, which is the statement I made. Yeah, I made here. So that's the inclusion of well, I made it in cohomology, but the exact same statement. If instead of lines I take C stars, exact same statement is true in W statement K-theory. So this is so maybe this is the equation. The set is defined by the equations 1 minus x over I equals 0. Any questions about this? And so then that then brings Then brings a question is to, like, if I have more generally, if I take say more generally G. Well, you can phrase this question very, very generally, but let's be slightly more general. More general. And you have G, now V, over V, which is representation of G, of reductive group G. G. Then you can consider, then you can study. So then maybe it has some normalizer. So maybe this sits in its normalizer. So there's a normalizer of G inside GLV. And then you can study the question of, so then there's a restriction map. You take the K-equivariant normalizer of G equivariant K-theory of V, and this restricts. There's a map from this. You take normalizer of G mod G equivariant K-theory of V minus unstable mod G. So there's this natural map, and then you can ask about interpolation as extending. So this is interpolation problem. Right, and similarly in cohomology. So this is if I have a K-theory cohomology or elliptic cohomology class on a GIT quotient. So this is also denoted by V mod G. When can I lift it? When can I extend it in some canonical way to the ambient stack? So this is a good question. Good question to study.
What can we say in the case of G is trivial?
What?
Let's consider a case when G is trivial group.
Well, then it's an identity map.
No, because we remove zero.
No, but the stable locus, you take the stable locus for a trivial group, zero is stable.
I thought everything which orbit contains zero is unstable.
No. This is in projective space. This is this projective space formulation.
Okay.
Yeah. Right. And then maybe we'll postpone it for a second. And the question is, where our Z's are going to come from? From in elliptic situation. This is a situation that interests us most. We need some kind of Z, and Z will have to come from peak. So and I claim that there is a map. There's a natural map from characters of G, the group by which you mod out, maybe tensor your elliptic curve. There is a natural map to peak of V mod G. Peak of elliptic homology, sorry. Peak of elliptic homology of V mod G. Right. So for every character of the group, there's if you tensor with elliptic curve. So previously we had an elliptic curve, but then we had a group. So previously in our example, with P1, this was the characters of the group. That was just Z for G equals C star. And so then it was just elliptic curve, and there was a natural map to the peak of that, a line bundle for. And this is not mysterious. This is because if I have a line bundle, well, maybe I can't explain everything. This is not mysterious. It's natural map. And that means from the characters of the variable Z gonna come from the characters of the group by which you mod out. And then this means in those parameters you're going to have some kind of elliptic expression that will have some poles. It will have interesting poles. So it says interesting poles. Poles having to do with certain root of the space V1, G. So this is the poles, they have a certain, in fact, these poles will be some abelian subvariety, so they will look, some kind of arrangement like that. And this will record some interesting information about this quotient space, which is maybe wasn't so particularly interesting for projective space, but for other spaces it will be very interesting. And then in the limit, this will become walls. Various walls in K. So I like walls. Well, I like poles even better than walls. But I don't know, some of you may remember with Dima we had this, what I thought was lovely midrasha a couple of years ago. That was already, what was that, like 3 years ago, and we had on the poster we had walls of Jerusalem, which is very, very nice with various kind of patterns resembling what I'm drawing here. But anyway, this is interesting things to consider. But so we will let this simmer for a while, and instead talk about integrals. Oh no, sorry. Before, so maybe for example of the kind where this is direct example. So previously we looked. So projective space was what, when we looked at column vectors. If I don't wanna again. So if we take column vectors with the action of A on this side and the action of X in C star on this side, right? So that was the projective space. Instead, if we now promote this to instead of matrices, so maybe there was N, so now N by K matrices, and we mod out by the action of GLK on this side, then the unstable locus are the matrices. Unstable locus, this is the locus where rank of the matrix is less than K. So here the locus was was 0, so rank 0, and here's less than K, and then you take the corresponding quotient X, well, let's say maybe V mod G in this case with module K here. That's the Grassmannian of K-dimensional subspace and N-dimensional space. And then the corresponding interpolation problem is also very classical one. So this means interpolation means interpolate a symmetric polynomial in variables x1 through xk. So this is, we are now, since there's a GLK, we have now a symmetric polynomials in k variables from its values at a point points where xi are a subset of the set AJ. Previously we looked at the situation where x is one of the i's, but now we look at the situation where these are distinct. So these are xi is a distinct subset. Is a k element subset of A1 through A. It's a very, very classical problem. And in fact, so this has some very nice distincts. The corresponding Newton interpolation polynomials. So we talked about Lagrange type of interpolation where and then there's also Newton interpolation. So the corresponding Newton interpolation polynomials, those are the classes of Schubert cell. So there's you can not only phrase the whole Schubert calculus, but in fact do it very effectively in the kind of interpolation polynomial language. So this is maybe something to maybe slightly more advanced example than we had from the beginning. So now talk about integrals. So integrals will have to do. So if I have a K-theory class, I can ask about, so if there's a push forward in K-theory. So if I have a bundle in KG of some, whatever, I forgot what denoted, X, I guess. This pushes forward to its what Euler characteristic, namely the alternating sum with cohomology. And that's an element in KG of a point. So group will continue acting on this cohomology space. So that's the push forward. And this push forward in the situation for quotients, for when X is a quotient, when X is a quotient, as JIT quotient, or maybe more general kind of quotient, just write a quotient. This can be expressed by ordinary integrals that eventually they come from Weyl integration formulas. So maybe I'll do again. I'll do again the most elementary example. So EG would take projective space. So let it before as before. Therefore, let X be projectivization of space. And then if I'd like to compute the Euler characteristic on this space of a line bundle of, let's say, D. So this O of D, these are the O of 1 it's the line bundle whose fiber are the linear functions on the line itself. Projective space is a space of lines. And if I look at linear functions on lines, this is another line, and that's O of 1. And so this means polynomials of degree D. Degree D, or maybe more somehow, also say this is the D-symmetric power of the dual vector space. And if I want to compute its character, and so the character as A module. So how does A act on polynomials of degree D? Well, this is the as A module. To enumerate all monomials of degree D, we can say, well, this is the coefficient of X to the D in 1 over the product of 1 minus X over AI. That makes sense. So this will, if I take a term of degree D, this will enumerate all possible monomials, and the weight of each monomial. Remember, this is the weight. My line bundle O1 is the dual of the line itself, so the weights are inverted, and so each monomial will enumerate exactly all monomials. And I can write it. As of course, as an integral 1 over 2 pi I. Integral around X equals 1. X to the minus D dx over X. This thing. Right? Everybody agrees with that?
Yeah.
And then more generally, this O of D here is exactly traceable to this term. So if I'm, more generally, if more general, I want to compute more generally. I want to compute the Euler characteristic of on PCN something that will be the same kind of integral. Let's see if I can copy this now. No, sorry, my copying functionality is not working today. I don't know why.
It's faster to rewrite.
Yeah, well, anyway, I'll just so okay, it's not copying today. Not sure why. So then there's a sum function or the corresponding function. And the interpolation issues will come when if I want to compute this integral by residues of this integral, they will, of course will go head to head with interpolation. If I want to know, if I want to compute, somehow the residues of an integral is exactly the point at which f evaluates. That's exactly the thing. And then more generally, chi, if I want to take the Grassmannian k-dimensional subspace and n-dimensional space, something, then the similar kind of thing I'll be doing is
something is a group.
Torus.
What? This something is kind of torus. What are these three dots?
Well, some K-theory class. Now this is says I have some. So that's a K-theory class, and the K-theory class corresponds to some Laurent polynomial. So this
okay.
This is a
that's what
K-theory class.
In respect some group G.
Right, and that exactly, yeah, and then the corresponding Laurent polynomial.
Okay.
It will come here. And so then similarly, here that will be what will be the integral on. So at least I think it at least lets me move. So moving is fine. So I'm just not copying. So what's it going to be? It's going to be 1 over 2 pi now to the power k. Well, maybe not so important. Then 1 over k factorial, the order of the Weil group. Just explaining the structure of Weil integration formula.
Yeah.
Weil group. Then there will be the product of dxi over xi. And then there will be the term product over I not equal to j, 1 minus xi over xj, divided by the product over I j, 1 minus xi over aj. This sort of thing. Where this comes from the representations from the action on n by k matrices, and this is really the Weil character formula here. Sorry, Weil integration formula. Okay. And now if we want to compute an integral, and then there's a function, right? Sorry, most important thing. And then this thing here becomes some kind of function here. Maybe we'll just write f of x. This function corresponds to some K-theory class with some Laurent polynomial, which is taken in here. And if we were to it's clear that we want to compute some integral like this by residues. It's clear that the residues are These are exactly where set xi is exactly k-element subset of the set A1 through n. And the fact that they have to be distinct is because otherwise the numerator will vanish. Sorry, I'm giving like a grade school explanation for this, but it's you see if I pick two of the xi's to equal the same ai, then the numerator will vanish. So. And so, what will transpire in some second part of this talk is that we will not be computing integrals by rest. We will keep them to be over unit torus. We will use integrals like this to solve interesting, or I hope so. Well, at least other people think it's interesting Q difference equations. Such as, what are examples of interesting Q difference equations? Such as QKZ equations associated to some quantum groups and similar kind of objects. So they're all yes.
To solve means to write integrals, represent solution and then some kind of integrals.
Yeah, right. So write an integral solution. So generally speaking, this is if you have a Q difference equation that's just the same as having a differential equation. So if a differential equation, then we can talk about the importance of Q difference equation maybe in a minute, but let's just first have our feet on the ground. So if I have a differential equation, generally speaking, I don't expect it to have an integral solution. To have a differential equation to have an integral solution means my differential equation is something like Gauss-Manin connection for some family of algebraic varieties. So the question is, what does it mean for a Q difference equation to be a Gauss-Manin connection? That's an extremely interesting question, and this has to do with prismatic homology and other kind of really advanced things in mathematics. But it's also important in practical applications like QKZ. QKZ, an equation that comes in the analysis. I mean, QKZ and a similar equation come the analysis of solvable lattice models in statistical mechanics, for instance, and other objects. And to actually have an integral solution for them, if you have an integral solution, you do have things. So if you have an integral solution, you certainly immediately see things like monodromy, special values, and so forth. So, and the typical question about QKZ is to compute its monodromy. It means the typical physical problem. You have something defined in the neighborhood of one point that you'd like to compute in the neighborhood of a different point. That is, or in the world of Q difference equation, people call transport monodromy because, well, for reasons maybe actually in Jerusalem I gave a lecture about the monodromy of Q difference equation on the occasion of that midrasha. And where I at length argued, what is it? What kind of object is that? But anyway, so this is regardless of the fact that where this integral is going to fit or not fit in the eventual theory of Q Gauss-Manin connections and prismatic Gauss-Manin connections, something like that. Regardless of questions like this, it's still interesting to solve interesting equations by integrals. This also generalizes integral solutions. In particular, also, if you take if you Q difference equation, also the Q to 1 limit, this gives IE some kind of saddle point. That gives all this kind of beta ansatz. Because if you have a solution of Q difference equation, and by something explicit, then in particular, you know the Q to 1 asymptotics will give you the eigenvectors and the eigenvalues of the things you're solving. These are linear Q-difference equations. I should have stressed this. Interesting linear Q-difference equation. So even a linear Q-difference equation, if you let Q to 1, this means you're going to be finding eigenvalues and eigenvectors of whatever your matrix, and that's a generalizes question of diagonalizing Hamiltonian's very interesting lattice model. So it is an interesting question. Anyway, but we in the spirit of this talk, we will be with so two differences. Two differences is that the first difference, well, what does it mean to solve some equation by an integral? It means your integral is going to transform maybe a simpler difference module into your interesting solutions of Q-difference equations about modules over Q-difference operators. And an integral is just some particular operation on such things. And so this means you search to realize your module as a direct image of some simpler module. Okay, everybody agrees with that, I hope.
Yeah.
And so it must be the case that under the integral sign, you have to stick solutions of some simplest Q-difference equation. And so it means under the integral sign, you'd like to stick things like 1 minus xi over aj. Well, this is not solving any interesting Q-difference equation. Would better replaced by the Q gamma function. So this is Q gamma function of xi over aj, which is an infinite product over n, or maybe n bigger or equal to 0, 1 over 1 minus q to the n xi over aj. So this is a solution of interesting Q-difference equation. Well, what scalar Q-difference equations? This is the first thing. The first thing to do is you want to what we'll be doing could be integrating objects, not rational functions, but rather something involving Q-differencing. And from this, there's two things. First thing, that where does that naturally come in? This naturally appear in the study of K-theory, not of X, some variety, but rather of maps from, well, maybe C or affine line to X, right? Because if I have an action on the domain of this map with Q, so the coordinates on the space of maps are like coordinates on X, and also polynomials with values in coordinates. So if I have some coordinate on X, then I have, so this means some weight with Q. So if I have some coordinate, maybe I don't know, call it T here, and the coordinate W here, the coordinates on the space of maps is going to be like like W, WT, WT square, and so forth, this sort of thing, right? And they will all these monomials, they will carry an equivariant action more and more. So this will have the weight. This will have the weight Q. This will have the weight Q square, and so forth. So when you account for all of them, then you're going to get, instead of previously you get had a rational function, now you will have a Q gamma function. And the second observation about it is that here, if you look at this expression, poles, instead of being a finite set, if you want about poles form obviously geometric progressions. With denominator Q, right? So this is for every pole, since they all kind of repeat. There's the whole procession of these poles, and therefore, if you want to interpolate, therefore elliptic interpolation is important for this kind of integral. Because we would like to some function to take given values in not at one point, but in a whole sequence of points that differ mod q, and that's then natural to take elliptic interpolation for that. And then second point about this formula. Second point, it is good to have, always good to have balanced expression.
What is balanced?
Yeah, I'll explain. It means gamma function is a big function. It's a large function. I mean, both big in terms of its formula and also in terms of its values. It's a function that grows or decays quite fast. And so it's always good to have a balanced expression. If I have a Q gamma function,
okay,
W, it's always to have some kind of shift here. Maybe I'll call it like H bar W, where this is something shift. It's like in ordinary gamma function, if I have gamma function H bar plus X over the gamma function of X, well, this is like X to the H bar roughly. Its goal is, it's always to have these things balanced. And so, and the way to achieve this, okay, this may be, I'm sorry, I'm near the end of my time, so I'm making a slightly abbreviated statement. The way to achieve.
Achieve means to prove or achieve to guess.
So achieve this, the balancedness in some expressions. I would like some expression to be balanced. And the way to achieve this is to have X symplectic with H bar the way to the symplectic form. E.g. Instead of Grassmannians, much better think about T star Grassmannian, where H bar, or rather H bar inverse, to have H bar inverse scales for tangent directions.
And if instead of Grassmannians, I give you coadjoint orbit.
Yeah, exactly. This is everybody. So of course, you know, this is something new this is nothing new for people in Jerusalem, because that is having that kind of scaling. It's crucial for many things in geometric representation theory, but also purely from the point of view of special functions. It's also very good to have expressions that are balanced. Okay. Could this be, since the audience kind of evaporated, maybe this is a good place to stop. So before I lose, I mean, I thought I had 4 more minutes, but then,
you have,
but then people disappeared in large numbers, so I figured I saturated some limit.
I'm very sorry for a small number of people. Very interesting. Actually, I would be glad to discuss talk to you. So let's maybe set up some time next week to talk.
Yeah, sure, fantastic. But there's also part 2, right? We're not canceling that.
Yeah. No, I
okay. Okay. That's good to know.
If you have time, I also would like to. I mean, I have to go to another seminar now, but and it's my students, so I have to go. But maybe I will join you a bit. So I mean, this general interpolation problem. Can you give some intuition for when it fails, or is it somehow?
I'll give some theorem when it succeeds. I mean, usually it fails most of the time. Yeah, I mean, it's a miracle when it succeeds. So.
Okay, so this will be next week.
Yeah.
Okay.
I have a very basic question. Actually, I was lost for probably roughly half your talk or a little bit more. I lost you slightly after or around when you moved to Equivariant K-theory. Is there some basic place where I can read some of these things and get a feeling for examples?
Well, yeah, there's plenty of really good books about Equivariant K-theory, but also
no, I mean interpolation. I mean understanding what Equivariant K-theory is okay. I did not understand how it is related to what you were doing before.
Okay. But so this is I mean, it's a good thing to maybe just do that example with Grassmannian. Think of what is the spectrum of covariant homology of Grassmannian and how it sits inside. So Grassmannian is a quotient by GLK and has a GLN action commuting with that. And so this means it's going to sit the corresponding K theory is going to sit in symmetric polynomials in K variables, and then symmetric or not symmetric depending whether you take torus equivariant or group equivariant or whole GLN equivariant homology in the variable an. And if you just think about like what is it, what's the spectrum looks like and of that, then I think this will be very natural to lead in that you understand that this is just some locus where xi's happen to be the xi's are disjoint and coincide with some of the ai's. And so in particular, the question of extending K-theory class from the Grassmannian to the ambient stack is exactly the question of interpolating a symmetric polynomial from its values and some number of points.
Okay. So maybe two more questions. So the positive results you get, they always rely on some of the integral solutions, or
no, it's the opposite. The integral solution. So the integrand in the integral solution will be some interpolant. So this is maybe I tried to explain. I mean, I guess I tried to say this. So to have an integral, you need to have a good integral. You need a good integrand, and the good integrand has to be. So the good integrand is defined. Is defined on the stack, but it has to come from the stable locus, and so the thing you integrate will be interpolant.
I see. Okay.
Yeah.
Okay.
And I'm not going to make a big secret. This symplectic condition is what you basically need for this interpolation to succeed. Of course, you can sometimes succeed in other things, but I don't see any. I don't have any general supply of examples where it succeeds because I mean, the fact that you're for this interpolation to succeed, it has to be the case that certain bundles consistently have degree 0, and I have no idea how to prove it outside of the symplectic situation. Symplectic seems to me more or less the only kind of the only. I mean, I couldn't think of any other conditions. So that's so this is so next time we'll start with taking a group and a symplectic representation. So that's
okay.
That will be the start of next lecture.
Okay, I have to also go to the next talk.
Andrei, so write to me when it's good time for you to talk next
week. Let's discuss it by email. I have to look at my calendar. Yeah.
I say right to me. Exactly.
Yeah.
Okay. Bye. Thank you.
Okay. Bye.
Thanks everybody. Thanks so much.
Very much.